Hello, everyone. Thanks for joining our nVent ReadyChem webinar. We're very excited to present to you today's topic, which is titled Energy Savings Benefits Using Smart Industrial Heat Tracing Controls. Now, energy and efficient ways to use it has been an increasing topic of conversation with companies in the industrial sector. So we hope this webinar will provide you with some helpful insights into how heat tracing can play a big part in this. Your presenter today is Jim Dawson from nVent. We also have Garrett Walsh on the line to answer the questions you might have. Now, as you can see on the next slide, these are the topics that we'll be covering. So we'll start up with a high-level overview of just general electrical consumption. We'll have some stats for you. We'll tie that into how electrical plays a big part. Heat tracing plays a big role in that. And then we'll kind of tie that in with heat tracing controls and defining what heat tracing control monitoring is about with some control types. And then we'll have some examples of energy savings opportunities with case studies that we put together for you. Then we'll wrap it up and then we'll open it up for Q&A. As a reminder, please use the control panel in front of you here to type in any questions that you have, and we can address them at the end. So with that, I'll hand it over to you, Jim.
All right, well, thank you very much, Eugene, and good day, everyone. Thank you very much for joining us today. We really appreciate the opportunity to present today's webinar on energy savings benefits using smart industrial heat tracing controls. So Eugene covered the agenda, so let's kick off looking at electrical energy use in North America. So in the USA, 3.9 trillion kilowatt hours of electrical energy are consumed in a year. And in Canada, 550 billion kilowatt hours of electrical energy are consumed in a year. Now breaking that down to the industrial sector, because that's where we're focusing today, 26% of that in the US is industrially consumed, and 40% of that in Canada is industrially consumed. And the major industrial users of electricity, probably no surprises, are the mining and primary metals, pulp and paper, chemical, and of course, oil and gas. So how does electric heat tracing play a role in that energy consumption? Well, as you're all aware, industrial facilities typically have heat tracing installed for freeze protection or for process temperature maintain. And it's there to keep that plant running efficiently. It's there should that plant have a shutdown, scheduled or unscheduled, again, to keep the processes flowing and keep the water from freezing. An electric heat tracing system consists of the heating cables, connection kits and accessories, and of course the power distribution and controls. Now, how big a role does it play? Well, we had the opportunity to reach out to a regional refiner here, and I am in the north, the Great White North of Canada. And the statement from that refiner was, pumps and compressors are by far the biggest users of electricity, but EHT is a significant factor. And at this refinery, utilized 20% of the electrical energy per year. Now, of course, this is all going to depend on your climate and your geography, on just how much of a factor EHT is, but obviously can be a very significant factor. So let's define heat trace control and monitoring just really quickly. Heat tracing control is the varying of the heating cable output to achieve the desired temperature. And typically, in simplistic terms, there's three ways we do this. We do this through self-regulating control, which is really just the installation of self-regulating heat tracing cable on pipe with a ground fault breaker, a power connect, and an end seal. We turn on that heat tracing circuit typically in the fall, and we turn off that heat tracing circuit hopefully in the spring. That's self-regulating control. We rely on self-regulating technology to vary the temperature. Ambient sensing control, one step further. This is where we are controlling the heat tracing with the outside temperature based on a set point. That set point could be 50 degrees F or 10 degrees C as an example. So when the temperature is Below that set point, everything gets turned on. When the temperature is above that set point, everything gets turned off. And of course, line sensing control. And this is where we're actually measuring the temperature of the pipe, and the heat tracing only gets turned on when the fluid in that pipe, whether it's a process or water, reaches the set point that's predetermined, turns on that heat tracing, and then when the process is flowing and warm, turns off that heat tracing. Line sensing control. Monitoring. Monitoring is the providing of feedback on the status of the heat trace system. And of course, monitoring is a key part of smart industrial heat tracing controls, because that's giving us the information on the temperatures, on the current, and of course, on the ground fault requirements of EHT installations. And the applications for EHT control and monitoring, we're going to talk a lot about freeze protection, keeping fluids above essentially 32 degrees F or 0 degrees C. And we're going to talk about process temperature maintain. And process temperature maintain can be broad control, depending totally on the process and the fluid that you're looking to maintain at a certain temperature. And it can also be a narrow temperature control if you have a critical process, a critical product that needs to be maintained to prevent freezing, crystallization, solidification, with sulfur being a great example that everyone's aware of. All right, so let's talk a little bit more about these controls. Self-regulating control by itself, great advantages, high reliability, no moving parts, lowest installed cost. But the disadvantages, obviously a wide temperature band. We're not really maintaining a tight process maintained temperature. The maintained temperature varies with the ambient. It's not energy efficient by today's standards. Self-regulating technology was developed by Raychem 50 years ago. So that is quite a while ago. Still a great technology, still used everywhere, but 50 years ago. So by today's standards, we need to think about other opportunities for energy savings. Other disadvantages, no feedback or monitoring when you're just using self-regulating control. And of course, if you're using lighted end kits, that's a great thing, but that really does just confirm continuity. It just confirms that things are turned on. Ambient sensing control. The advantages, simple to understand and install, low maintenance cost for a single thermostat. If you have a large facility with high density of heat tracing, even an ambient sensing control system can involve a lot of maintenance. The disadvantages, limited to freeze protection applications. The maintained temperature will still vary with ambient. And of course, it's higher energy consumption still than other control methods. And that's because if the set point, as an example, is 5 degrees C or 40 degrees F, power is always on to those heat tracing circuits when we're below that set point. And the power is always on at 100%. So again, ambient control when we're above that set point of 40 degrees F or 50 degrees F, click, everything goes off. And we're below that set point, click, everything goes on. That's really ambient control. Line sensing control. The advantages, tight temperature control at the location of the sensor, typically an RTD, a proven control approach, the lowest energy consumption, and the opportunity for centralized control settings. So of course, now we're measuring the temperature of the pipe. So we're measuring in a way the temperature of the water or the process fluid that's within that pipe. And the heat tracing is only coming on when the flow in that line stops, the pipe begins to cool, the process cools, and heat is required. That's line sensing control. Obviously, the greatest energy opportunity, one of the greatest energy saving opportunities. The disadvantage is RTDs are required for that temperature measurement. And so that means a higher installed cost because you have the costs associated with the installation of the RTD, the cable, the conduit, the tray, the connectors, the labor, etc. Now, there are options like the RMM2, which can consolidate RTDs and bring that information back in less wiring. That potential exists, but it's still a higher installation cost. And sometimes it's a challenge on existing installation that was not installed or designed as line sensed. Very easy to do at the beginning and at the design stage. It is possible to achieve line sense control, however, without RTDs. And I just wanted to spend 1 minute explaining that you can use an existing thermocouple or thermal well to get a temperature back to a heat trace controller if you have an industrial EHT controller capable of accepting that 4 to 20 milliamp signal like the Raycam Alexa 4000 series. So if you have an application and you want to upgrade from no control or ambient control to line sensed without all the significant costs of moving to line sense, which means removing insulation and cladding and installing RTDs, very often you'll have existing thermal wells or thermocouples that you can then grab that signal and set up yourself with a line sensing application. And in fact, it's the ultimate in line sensing application because you're actually measuring the temperature of that critical fluid as opposed to the outside temperature of the pipe. So there is an opportunity there. So the current focus today of EHT control and monitoring is typically around maintenance. So preventative maintenance programs and safety with, of course, ground fault. Operational, we need to maintain the process conditions, and we get that information and that feedback through monitoring and the alarming and the communication and the connectivity of smart industrial heat tracing controls. And of course, most important, the reliability. No frozen lines, very important. Maintain non-flowing process temperatures and prevent unscheduled outages. That's really the current focus of EHT control and monitoring, and that's certainly a very good thing. And how we manage that focus today? We manage it, as we've discussed, through ambient sensing and through line sensing. And that can be done with mechanical and electronic thermostats, as an example, as one way of managing that focus. But again, we're talking about simple on-off. We're not talking about smart control and monitoring and the opportunities that come with using smart industrial heat tracing controls. It's very, very common that we utilize freeze protection panels. So a dedicated power distribution panel for the heat tracing system, typically on ambient control. So again, now we're talking about when the temperature drops below that set point, that might be 50 degrees F or 10 degrees C, click, everything comes on in the panel. And when we're above that temperature, click, everything goes off. So we're really still talking about on off, and we're talking about 100% on when we're on. So freeze protection panels, very common, very popular, but not really helping us achieve some of the energy saving benefits that are out there. And of course, EHT smart controllers that I'm sure you're very familiar with, typically, typically individual 1-to-1 ratio of controllers to circuits, or group, multiple circuits controlled by an individual device. Lots of options, lots of opportunity for very large installations if you have a facility with a high density of electric heat tracing. And of course, now the benefits of control and monitoring. EHT smart controllers offer us the control modes and features that provide us the opportunity for energy savings. And that's really what we're here to talk about today. Those control modes, again, ambient control, we've already talked about. Proportional ambient, we're going to talk a little more about. Line sensing, we all understand. And the opportunity to use a digital input capability, a digital input feature as part of an EHT smart controller. So energy does matter. And we truly believe at nVent Thermal that energy is going to become even more and more important in the coming years. We're going to hear a lot about it. And when we think about the control modes that we've talked about and the opportunities we've talked about so far, no control with self-regulating cable, again, power is on 100% when that GFI breaker is on, and that's typically September to April. Not really doing anything from the standpoint of reducing energy consumption. Ambient control, we talked about. Thermostats, freeze protect panels. In this scenario, no monitoring, and as we discussed, the power is on 100%, when the ambient is below the set point, which could be 50 degrees F or 10C or 40 degrees F or 5C. These are all common set points used for ambient control. Now, of course, ambient control is an available control mode in smart industrial heat tracing controllers. And when used in that case, you have the benefit of full control and monitoring. But from an energy standpoint, the power is still on 100% when the ambient is below that set point. Proportional ambient control. This is a control mode that provides us with opportunities for energy savings. And we are going to look at some case studies to review that. Proportional ambient control, again, requires smart industrial heat tracing controllers, but this control mode varies the power output to the cable based on the ambient temperature. So proportionally varies the power to the EHT cable based on the ambient temperature. And we'll talk more about that. And of course, line sense control, typically using full smart industrial heat tracing controls, all the features and benefits of control and monitoring. Power to the cable is only on when the temperature calls for it. We're going to take that one step further and talk about the opportunity that digital inputs can provide to maximize energy savings in a heat tracing installation. So let's have a look at some case studies that demonstrate these opportunities quite clearly. The first case we're going to talk about is self-regulating, no control or self-regulating control scenario at a facility. And this facility was owned by a regional oil and gas producer who reached out to their site electrical contractor looking for energy savings ideas. And as I mentioned earlier, at nVent Thermal, we believe that a lot more people are going to be looking for this opportunity to reduce the energy costs, especially electrical energy costs at their facilities. So currently with this oil and gas producer, no control self-regulating EHT is the site standard. What does that mean? That means that this contractor turns on the GFI breakers in the fall and turns them off in the spring, and all winter long, the self-regulating cable does its job. The contractor took on the initiative to perform a study around this EHT, around this self-regulating cable. They measured the EHT power consumption over the entire heating season. And with that information and with the cost of power for the customer, they calculated the potential savings with the installation of ambient control. So really just one step up to thermostat control. What they found shocked them a little bit, but essentially on a mild day, right around freezing, and processes that operate at 21 degrees C or 70 degrees F, that the 10 watt per foot self-regulating cable that they had installed throughout their facilities was still putting out over 7 watts per foot. Now, that's exactly where we would expect it to be based on one of our 10 watt per foot cables that you see on the right-hand side at 21 degrees C or 70 degrees F. We exactly expect just over 7 watts per foot. So what that means is, as we mentioned earlier, self-regulating cable is putting out power all the time, all winter long, on a flowing process that's at 21 degrees C or 70 degrees F. So this contractor then, with the data from the owner, developed a chart outlining the potential savings for the different scenarios within this oil and gas field. And whether that's a 4-well pad or a battery and gathering facility, varying the amount of heat tracing used at these different facilities, you can see that the significant annual savings just upgrading from self-regulating no control to thermostat ambient control. And the contractor also made it very clear to the owner that line sensed would it even lead to greater cost saving potential from an electrical energy consumption standpoint. Let's look at case study number 2. This is currently an ambient thermostat control facility. It's a mine site in northern Saskatchewan, Canada. The heat trace cable they use is an 8 watt per foot cable, and they standardize on 300-foot circuit length. They use 6-inch pre-insulated pipe, 2-inch insulation. The SR cable is in channel, and the maintained temperature is 5 degrees C or 40 degrees F. Very, very large facilities. Their current control mode is ambient using thermostats. So as I mentioned, when we're above the set point, which in their case is 40 degrees F, click everything's off. When we're below the set point, click everything's on. And when it's on 100%. And in a northern climate, like where I am, that means the EHT is typically energized for the majority of the year. Let's think about using smart industrial heat trace control and a control mode called proportional ambient. Proportional ambient, as mentioned earlier, proportionally varies the amount of power being sent to the heat tracing cable based on the ambient temperature. In ambient control, and under these conditions, where the minimum ambient design is minus 58 F or minus 50 C, that means that heat trace cable is designed for a temperature that might exist 2 or 3 days of the winter, certainly not the whole winter. So a lot of energy to be ready for that minus 58 F. Proportional ambient varies the power proportionally to that cable based on the outside temperature, saving a lot of energy for the installation. This table summarizes the potential power savings for this facility, and this facility is currently looking at this installation. You can see in the middle column, the power consumed every month by one circuit is pretty much the same. And again, it's a cold climate, so the heat tracing is pretty much always on. If you look at proportional ambient and you look at the duty cycle on the left, you see each month the amount of power put out to that heat tracing cable varies based on outside temperatures, and it's never 100%. So the power consumed with control, the column on the right, as you can see, also varies. And at the end of the day, it was identified for this facility that the potential savings on energy, electrical energy for heat tracing, is over $1,000 per heating season per circuit. And at this facility, and many like it, you're talking hundreds of heat tracing circuits. So a great opportunity to save electrical energy by installing smart industrial heat tracing controls and using proportional ambient control on an existing ambient control installed system. Let's look at case study number 3. Case study number 3 is a line sensed energy saving opportunity. This is a regional refinery at the design stage. So this work was all done at the design stage, which is the right time to be looking for line sensed opportunities for sure. This refinery is also in a little bit more of a moderate climate. You can see from the chart on the left that the winter months, you're typically right around freezing. You're not at minus 50, but you're around 0 C or 32 F. And so it might be a little bit more representative of the market or the geography you're in. At the design stage, this refinery had 32,000 feet of heat trace pipe. The maintained temp was chosen to be 40 F or 5 C. The percent of the year that we're below that set point is 58%, and the process in flow condition is 75% of the time. Energy cost, 10 cents per kilowatt hour. Looking at this refinery and all of the heat tracing, and remember, a refinery is going to include both MI, constant wattage heat tracing, and of course, self-regulating heat tracing cable. In an uncontrolled scenario, heat tracing comes on in the fall, off in the spring. We're talking a cost of about $132,000 a year for the energy cost. By just moving up to ambient sensing, so now only turning on that heat tracing when the outside temperature is below 40 degrees F, you see a 42% reduction in the cost of heat tracing energy, down to $77,000. And by looking at line sensing as an opportunity for heat trace control and monitoring, you're now looking at a 97% reduction in the cost of energy for the electrical heat tracing at this refinery, down to $3,000 a year. So a great opportunity using line sensed and achieving the benefits, the greatest energy saving benefit with line sensed. Now let's take that one step further and see what can be achieved in certain scenarios with a digital input. And in this case, the digital input is from Flow. So let's look at some basic points first. Heat tracing is designed to maintain the temperature of a fluid in a non-flowing pipe. Self-regulating heat tracing power output is based on the temperature the cable sees. Processes are typically flowing, and SR cable watts per foot output ratings are based on 50 degrees F or 10 degrees C, as we saw earlier with the data from the contractor. So there are scenarios where the fluid in pipe can be cold or cool, forcing the SR heat trace cable to operate at a high watts per foot output on a flowing pipe. And in fact, we know from the earlier example that even 7 watts per foot are being put out by a 10 watt per foot cable on a 21 degrees C line or 70 degrees F, which I guess we could classify as cool. Examples of cool water applications: influent water from lakes, rivers, and wells, gas lines, cooling water, utility water, and of course, cryogenic processes. So if we think about how we can use a digital input feature and take a signal from a flow meter and inhibit the EHT from being on in these applications, there's a significant opportunity for energy savings. A local scenario that I was involved in involved an oil and gas facility with a 30-inch influent water line. As you can imagine, a very large oil and gas facility. That line had 9 passes of MI and was line sensed. Well, for more than half of the year, the temperature of that influent water was below the set point of the line sensed control. So that means 9 passes of MI cable on full load the entire time that the water coming into this facility is cooler than the set point. Now, of course, that heat tracing has to be there, because should that flow ever stop, this is a pretty important line to this to any facility, influent water, but there's got to be better ways to save energy in that type of application. So let's look at a case study, a recent case study, actually, where digital input was applied. This is a diamond mine in northern Canada. 7-kilometer long line, 4.5 miles, 22-inch diameter line in the Arctic, essentially. Line sensed with the set point being 5C or 40 degrees F. This facility uses SC cable, so it's a constant wattage cable. It's not self-regulating. The water temperature is less than the maintained temperature, basically year-round. So what the site did, working with their local people, is used a digital signal from a flow meter to override the smart industrial EHT controller and inhibit the heat tracing when the flow is on. The site investment to achieve this change and use this feature was $67,000. The site energy saving is greater than $900,000 per year. And this is largely because this site uses diesel to generate their power. So a huge opportunity, obviously not the same type of opportunity everywhere in North America, but again, demonstrating the benefit of using a digital input, in this case from a flow meter, to ensure that the heat tracing is only doing its job when it needs to do its job. And in this scenario, because of the distances, wireless technology was incorporated to get that digital signal from the PLC to the remotely mounted heat tracing controllers. A huge savings opportunity. So to summarize, there are significant opportunities to save energy using smart industrial heat tracing controls, especially when you think about no control with self-regulating cables only, even ambient control, where it's just on-off based on an outside temperature, but all of the heat tracing is on when you're below that set point, and majority of those lines are flowing and doing their thing, not really needing that heat tracing to be on. It's there. It's there for the emergency. It's there for when the plant has a scheduled or unscheduled shutdown, but not really necessary the majority of the time. Proportional ambient control, a great opportunity to adapt an ambient control facility using smart industrial heat tracing controls, taking advantage of a control mode called proportional ambient, and now only putting out the power to those heat tracing circuits that's required should the flow stop based on the outside temperature, which is not always minus 50 degrees C or minus 58 degrees F. And of course, the ultimate opportunity for energy savings is line sense control. And taking that one step further, in the case of the diamond mine, using digital input to really ensure that that heat tracing is only there to do its job when absolutely required, as opposed to being on all the time on a flowing line. Thank you very, very much for this opportunity. Really, really appreciated the time and the opportunity to talk to you about energy savings opportunities with smart industrial heat tracing controls. Back to you, Eugene.
Hey, thanks, Jim. Those were some really great examples. So let's open it up for any questions that you might have right now. So please, as a reminder, use your control panel and type in your questions. Garrett, do we have any questions on the line so far?
We do, yeah. First one from Dave Oschek in Colorado. Is there a plan to provide a calculator worksheet to show customers the energy cost savings? I think that's a great idea. I actually didn't have that plan, but I think that is something that would be important, that we need to put a number in front of this. You know, one of the things specifically this year that we're starting to receive feedback on from our customers, for a lot of areas, especially, you know, I'm based out of Houston, and a lot of times the response from customers here in Texas was, well, the price of electricity is so low, you know, it's not really that big of a concern. But just this last year, we had a very bad freeze where the Texas power grid was actually offline for a lot of parts of the state for several days. And the response we're getting back from customers afterwards is, hey, my electricity rate shot up. This is now something that I'm very interested in. So even if you've had this conversation before, I think it's important that, you know, that you might want to retread old ground, and you find, you know, your customers is more than willing to listen now. So I think, yeah, putting a calculator together would be a really good asset. Next question that popped in here, what is the difference between freezing temperature and maintenance temperature? That all depends on what your process fluid is. For a lot of these applications, it's either going to be water, or you might be heat tracing a instrument air line where you're just trying to prevent condensation from freezing inside. Typically on those circuits, you know, water will freeze at 32 degrees Fahrenheit, 0 degrees C, and we would maintain at 40 degrees Fahrenheit, or generally about 5 degrees C. But if you have a different process, that may be different temperatures. Generally, though, we like to set the maintain at slightly above whatever the freezing temperature would be, just because in the event that the heat trace isn't working for some reason, say you have a portion of the pipe that's missing insulation, all of our advanced controllers have a low temperature alarm, assuming that you have an RTD on the line, or a low current to determine that the heat trace may not be pulling the right amount of current, so it's not heat tracing. And that in that case, we like to set the main there just to give us some time to recognize that there may be a problem before you have a freeze. Next question here. Let me see if I can open this. What if a customer wants to look at 3 or 4 controls on a single line using a thermal well? Do the controls have a way to see the energy expended per month per day? So one of the interesting things that we've actually come across with one of our clients is here in Louisiana. They're a tank terminal company, and the way they operate is they essentially have a large tank farm that they will rent out, and then the different local chemical plants, refineries, or docking loading stations will rent out their tanks in order to store, different hydrocarbon products for several weeks or months at a time. One of the successful things that they've been able to implement, specifically here, this was on the NGC 40, is they've been able, using Raychem Supervisor, to capture how much energy is being expended on a per circuit basis. And so they know for a given tank, they might use however many kilowatts per month. And because they're able to pull that data, they've actually been able to go back to the customer and add that as essentially a weekly or a monthly fee of this covers the energy expenditure that they have. So they've actually been able to use that as a revenue generator for them. Next question on here. Explain the difference between ambient and proportional ambient control. That's a good one. Jim, if you're still driving the presentation, would you mind going back to first of all, the slide with ambient and proportional ambient? Perfect. Yeah, there we go. So for ambient control, this is also called what you might hear as deadband as far as a control mode goes. The way this works, all of our controllers operate on a what's called a positive deadband, meaning if here in this example, it shows a set point of 50 degrees. So as long as the RTD, whether that be a line sensing RTD on the pipe or an ambient RTD that's just measuring the ambient air temperature, as long as that temperature is 50 degrees, the heat trace will be on, and it remains on until that temperature hits a point at the set point temperature plus whatever your deadband is. So in this example, let's say you have an ambient RTD, it's measuring just the ambient air. It's starting to be the fall, it starts to get a little cold, and at night it hits 50 degrees. At that point, the heat tracing would kick on, and it would remain on until that ambient RTD read 54 degrees. And it does that because you have a deadband of 4 degrees. That deadband can be adjustable, so you can increase it. By default with most controllers, it's 5 degrees Fahrenheit or 3 degrees Celsius, but you can adjust that to be larger or smaller than you want. But when I say it's positive deadband, it will never, you'd never have to worry about it getting your set point temperature minus your deadband. The heat trace will always remain on at your set point, and it remains on for set point plus deadband. So as you can see, it will cycle on and off as that RTD that's controlling it as the temperature changes. How that differs from proportional ambient control is here for circuits that use a solid state relay rather than an EMR. We can use proportional ambient control, and what that will do is the RTD still communicates whatever temperature, ambient temperature, to the controller, but the controller can essentially create a duty cycle by cycling the circuit on and off multiple times per second, it can determine what is the amount it actually needs to stay on to try and keep a very tight temperature control. So you see there, what will happen is at 40 degrees Fahrenheit, your duty cycle is 0, so your temperature starts to decline. And as it starts to get colder, that duty cycle increases. And so what it's trying to do is it's trying to flatten the curve, where it's maintaining a duty cycle that will be what is the minimum amount of energy that it has to be on in order to maintain essentially a flat, either for proportional ambient control, it knows how much current and how much heat output that specific circuit needs in order to maintain at least your set point value without expending additional. So the difference here is with ambient control, it's either off 100% of the time and on 100% of the time, and it cycles between that. Or with proportional ambient control, it's cycling multiple times per second so that you get an average duty cycle of 35% or 65% or whatever it needs to. Next, we had a question: which of our controllers have the input to inhibit EHT power based on flow? So the controllers that have that are the Alexent 4010, Alexent 4020, NGC 40 has a dedicated input, and that is it as far as just a simple dry contact or a handoff auto or anything where it's just a simple voltage source to indicate flow. You can still get that on an NGC 30 or a 920 controller, but that would need to come in the form of a Modbus signal rather than just a simple voltage, no voltage. Next question. Remember, if you have proportional and have an in sealed right, be ready for a lot of blinking. Yeah, that is a good point. If you are using lighted in seals, whenever you have deadband, since it's on, and by deadband I also mean this on-off ambient control. Whenever you have those lighted in seals, since it's either on or off 100% of the time, it's very clear to see, when the circuit is on, when the circuit is off. If you have those in seal lights and you have proportional, since it's cycling multiple times per second, it can look like that light is blinking. So that's something that you need to be aware of. If you're worried about energy consumption, I would suggest either, and you want to use proportional ambient control, I might suggest going not using lighted in seals, because a lot of times maintenance crews that may not be familiar with that, they may be confused by seeing a blinking light. They aren't sure what that means. So you might be better off either going with a standard, above the insulation in seal, or just sticking with on-off ambient control and maybe adjusting your deadband to be slightly smaller to lower your overall energy consumption. Next question: what is control with limited? If I understand this question, what is control with limited? Do they mean line sensing, or I'm not sure. Suradran, do you mind? Would you mind rephrasing that question? I'm not sure what you're asking. RTD sensing. So if I understand, what is control with RTD sensing in the software? What is RTD sensing in the software? Sorry, I'm not sure I understand that question. Yeah, if you wouldn't mind retyping it, I can get back to that. Question from Ian Henry: with PASC, do different heaters adjust it differently? Yes, it does. Proportional ambient control, it will, whenever you're using it, it will understand what heater output you have, as far as, if you have SR cable are using 5 BTV, 10 BTV, 20 BTV, as well as what is your minimum ambient for the area, what is the insulation type and thickness you're using. All of that is inputs that's used during heat trace design. So whether that's nVent is designing that, or if you're using TraceCalc Pro, a local user is using that. All of that is inputs that go into the controller's decision for what duty cycle needs to have at any given time. So all of those are things that need to be known ahead of time in order to use proportional ambient. Next question, TraceCalc Pro, there is a control section in this RTD sensing. So, and my apologies, maybe I'm just not understanding this, but if I understand what they're saying, there is a control limited design. Control with limited. Control limited design, what that means is whenever you're using TraceCalc Pro to design a circuit, one of the things that we need to be aware of whenever we design those circuits is for some areas and some fluid processes, there are things that we need to be aware of whenever we're approaching T-class or AIT concerns. Generally, this has to do with hydrocarbons, where you would have, say, for example, crude oil or any sort of flammable type process where you actually can't get, the heat trace can't get too high of a temperature. And it's a safety requirement. So the standard of that is always, if you're working in a refinery or any type of oil and gas plant, a lot of times for a given area, there will be a requirement that the heat tracing can't exceed 450 degrees Fahrenheit, for example, or whatever value it is for that. Whenever you're doing control limit design in TraceCalc Pro, what you're saying is, rather than just having your heat trace cable on the pipe and you're controlling off of the ambient temperature, if you have a control limited design, that means you have an RTD on the pipe that's actually measuring pipe temperature. And whenever you do that, it makes sure that you're able to maintain a much tighter temperature window on that pipe, because you actually know what the temperature of the pipe is. If you're doing only ambient control, our heat trace circuits are designed for, worst case scenario, meaning the minimum ambient temperature for that area. But if your minimum ambient temperature is -40 degrees and it is 39 degrees outside with a set point of 40, you may be heat tracing more than you have to. And your heat trace temperature may be a concern with that, either the AIT or the T rating of the area. So that's what that control limited design is. Next question, is this presentation available on Partners Corner? We are recording this, and I believe this will be shared afterwards. Eugene, are we planning on posting the actual presentation to Partners Corner as well?
Yes, this presentation is being recorded, and for our channel partners who require the actual presentation, yes, I'll make that available as well.
Next question here. We saw controls with SR cable. The same scenario would be applicable with MI cable as well. Yes, it would. So for the scenarios we were looking at, MI cable even more so. SR cables are self-regulating, meaning they do dial, their heat put adjusts with pipe temperature to some extent. It's important to know that you never get to zero heat output. Even on a hot pipe, you will be drawing some current. There will be some heat output, and you're going to be using some energy. It's just going to be less on a hot pipe than a cold pipe. For MI circuits, however, your heat output is relatively constant, regardless of pipe temperature. So not only for the scenarios we've been talking about today when it comes to energy savings, not only is that also applicable to MI cable, I would say it's even more so, because with self-regulating, you at least get some amount of decrease in energy consumption whenever you have a hot pipe. With MI, you don't get that benefit at all. So really, this is all of these energy savings are going to be more effective on MI circuits. And that was all the questions we have in the chat. Oh, one more. Not directly related to the energy savings discussion. Has nVent seen interest in a JBM3 for 3 runs? I'm thinking tank applications could see a benefit. I'm not sure when you say JBM3, the standard JBM does allow for mid-feed or having multiple heat outputs. So I'm thinking this may have to do with having 3 different runs or 3 different heat trace cable outputs from a single JBM. And I would say there are okay, yeah, I said that. That's correct. There are applications, yeah, specifically like for tanks, where that's definitely a benefit. That's actually something that we are looking into. One of the things that we have to balance that against is anytime you have 3 different heat trace cable outputs from a single JBM, that you have to know that the entry into the JBM is real. The size of that has to be adjusted to what power wire that you're bringing in there. And for a lot of applications, you know, this is the JBM. I think it will allow for JBS, and the JBM today allow for an 8-gauge wire. Now, if you have 3 different heat trace outputs out of that JBM, but you only allow for an 8-gauge wire for the power input, the distance that you can have for each individual run, if you're having 3 of those, is pretty limited. So could a JBM with 3 runs be possible? Yes, but we would need to increase the size of the power entry, which increases the size of the enclosure. It increases basically everything upstream of that. So that's something that we have to balance whenever we're designing that, is making sure you know, we have a JBM that would have the ability to have 3 runs without making it, you know, the size of a mini fridge, for example. The enclosures just start to get larger and larger as you have more and more heat output for each circuit. All right. And with that, give it maybe a little bit, but I don't see any other questions in there. So hopefully I've been able to answer all the questions that everyone has. If not, please feel free to reach out to me with any questions. Again, my name is Garrett Walsh. That's garrett.walsh@nVent.
Great, thanks, Garrett. So Jim, I believe this wraps up our session. So we hope this was informative for everybody. Once again, if you have any additional questions, please reach out to us or contact your local nVent expert, and they kind of walk you through some of the scenarios that you may have at your facility. So just kind of a reminder that we have future webinars on schedule. If you visit us at www.nvent.com/thermal-webinars, you can view some of our previous recorded webinars as well, in addition to our upcoming ones. So that wraps it up. Thanks, Jim. Thanks, Garrett. Thanks, everybody. Have a good day.
Yeah, thanks, y'all. Appreciate everyone calling in, and yeah, have a good rest of your day.